4 billion years ago, the sun shone 30% dimmer than it does today. This is not speculation. It is one of the most fundamental and well-confirmed facts in all of astrophysics, supported by thousands of independent observations of stars at different stages of their lives, and by our detailed mathematical models of how stars generate energy. If you take the atmosphere Earth has today, the same nitrogen, the same carbon dioxide levels, the same water vapor, and run it through a climate model with the solar energy output of 4 billion years ago, the answer comes back with brutal clarity. The global average surface temperature would be approximately -40 degrees Fahrenheit. The oceans would freeze completely. The ice would reflect sunlight back into space. The planet would grow colder still. It would enter a feedback spiral from which there is no escape. A permanent global glaciation that the models show could never thaw. Not in a billion years, not ever. Life would have been impossible. Now look at the oldest rocks on Earth. In the Jack Hills of Western Australia, there are tiny crystals of a mineral called zircon that are 4.4 billion years old, older than any other known piece of the Earth's solid surface. And locked inside those crystals, in the ratios of oxygen isotopes and in the chemical fingerprints preserved in their structure, is unambiguous evidence of liquid water. Not ice. Liquid water. 4.4 billion years ago, when the sun was at its most anemic, the surface of the Earth was wet. Physics says frozen. Geology says liquid. Both are right. And the 50-year scientific detective story that has tried to reconcile them is one of the most beautiful and still incompletely solved puzzles in the history of science. This is that story. Before we go any further, please subscribe to this channel. Your support really helps us to continue our work. Thank you. There is a concept in science called a paradox, and it is worth being precise about what the word means in a scientific context. A paradox is not a mystery, a gap in knowledge that will eventually be filled when we find more data. A paradox is a direct logical contradiction between two things that are both known to be true. The faint young sun paradox is a genuine paradox in this strict sense. The physics of stellar evolution and the geological evidence of early Earth both rest on solid observational foundations, and they flatly contradict each other. Resolving a paradox requires not just finding new information, but finding a new framework, a factor or mechanism that was left out of the original analysis and whose inclusion removes the contradiction. For 50 years, scientists have been hunting for that missing factor. They have found several, and the story of what they found and what they still cannot fully explain reaches from the nuclear furnaces of stars to the chemistry of the ocean floor, to the question of whether complex life can exist anywhere else in the universe. To understand the paradox, you need to understand how stars work. The sun generates energy through nuclear fusion, the same process that powers a hydrogen bomb, but controlled, sustained, and operating continuously for 4.6 billion years. In the core of the sun, at temperatures of approximately 27 million degrees Fahrenheit and pressures 300 billion times greater than sea level on Earth, hydrogen nuclei are being fused together to form helium nuclei. Each fusion reaction releases a tiny quantity of energy. But the Sun performs this reaction approximately 600 million tons of hydrogen every second, and the cumulative energy output is approximately 3.8 times 10 to the 26th watts, a number so large it defies ordinary intuition. The energy produced in 1 second by the Sun exceeds the total energy consumption of human civilization across its entire history by a factor of several million. The critical fact for our story is what happens to the Sun's core over time. As hydrogen fuses into helium, the helium accumulates in the core. Helium nuclei are heavier than hydrogen nuclei, and as the proportion of helium in the core increases, the core gradually contracts under its own gravity. This contraction releases gravitational energy, heats the core further, and increases the rate of fusion reactions. The net result is a Sun that grows slowly but continuously brighter over its lifetime, a process that is well understood theoretically and confirmed by observations of other stars at different evolutionary stages. The current best models of solar evolution, calibrated against helioseismology, the study of sound waves propagating through the Sun's interior, indicate that when the Sun was approximately 4 billion years old, it was radiating approximately 70% of its current energy output. When the Earth first formed 4.5 billion years ago, the Sun was perhaps 72% as bright as it is today. Over the entire history of complex life, the past 600 million years, the Sun has brightened by perhaps 5 to 6%. 30% less solar energy reaching Earth's surface is not a subtle climatic perturbation. It is a catastrophic reduction by any standard of climate science. The energy available from the Sun is the fundamental driver of Earth's surface temperature, and removing 30% of it would have effects that dwarf any climate event of the past billion years by an enormous margin. Climate modelers who have run the numbers with realistic atmospheric parameters consistently find the same result. A young Earth with the modern atmospheric composition receiving only 70% of current solar radiation would have had a global mean surface temperature well below the freezing point of water, with ice sheets extending to the tropics within hundreds of thousands of years of formation. And once that ice formed, the situation would have been self-reinforcing in the most unforgiving way imaginable. Ice is white. White surfaces reflect sunlight rather than absorbing it, a property measured by what physicists call albedo, from the Latin word for whiteness. Fresh snow has an albedo of approximately 90%. It reflects 9/10 of the sunlight that strikes it back into space. The dark ocean, by contrast, has an albedo of only about 6%. It absorbs 94% of incoming sunlight. The consequence of this difference is a climate feedback loop of terrifying simplicity. As the global temperature drops and ice sheets form at lower and lower latitudes, more and more of the planet's surface is covered in high albedo ice rather than low albedo ocean. This reduces the amount of solar energy absorbed by the planet as a whole, driving temperatures lower still, which causes more ice to form, which increases the albedo further, which drives temperatures lower. Climate modelers call this the ice albedo feedback, and in their simulations of a young Earth under a faint young sun, it acts like a trap. Once the ice sheets reach a critical latitude, approximately 30 degrees, roughly the latitude of New Orleans, the positive feedback becomes self-sustaining, and the models show no way to escape. The planet locks into what geologists call a snowball Earth state, with ice covering the entire surface from pole to equator. We know that the snowball Earth state is not merely a theoretical construction because it actually happened not in the Archean, when the faint young sun problem was at its most acute, but later in the Proterozoic eon, when a series of global glaciation events left their marks in the geological record on every continent. The Sturtian glaciation, beginning approximately 717 million years ago, and the Marinoan glaciation, ending approximately 635 million years ago, each covered the Earth in ice from pole to equator, a condition so extreme that glacial deposits from this period are found in rocks that, at the time of deposition, were within a few degrees of the equator. The evidence is unambiguous. Dropstones dropped by melting icebergs into tropical sediments, cap carbonates deposited globally in the immediate aftermath of the thaw, and the distinctive geochemical signatures of a planet that had been sealed under ice for millions of years. The snowball Earth events of the Proterozoic are the real-world confirmation that the ice albedo trap is not a theoretical nightmare, but a genuine geological possibility. The Earth did fall into it, twice. And the reason it eventually escaped, the reason the snowball Earth thawed rather than remaining frozen forever, was the carbonate-silicate cycle. Under the ice, volcanoes continued to emit carbon dioxide. With the surface frozen, there was no liquid water to drive silicate weathering, and no biological activity to remove CO2 through photosynthesis or shell building. The CO2 simply accumulated in the atmosphere for millions of years, building to concentrations perhaps 300 times higher than today, until the greenhouse effect became powerful enough to overcome the ice albedo feedback and melt the ice catastrophically. The thaw, when it came, was rapid and dramatic. Geologists call it a deglaciation event, and the global temperature swing from full glaciation to post-snowball warmth may have been among the most extreme in Earth's history, swinging perhaps 40 degrees Celsius over a geological instant. The fact that the Archean Earth never entered this state, despite facing a sun 30% dimmer than the sun that triggered the Proterozoic snowball events, is the paradox in its most vivid form. The Proterozoic snowball events occurred under a sun approximately 94 to 97% as bright as today. The Archean Earth faced a sun only 70% as bright. If the ice albedo trap was powerful enough to lock up the planet under a nearly modern sun, how did the early Earth avoid it under an even dimmer one? Something was keeping the Archean Earth not just above freezing, but warm enough to avoid even the conditions that triggered the Proterozoic glaciations. That something was the greenhouse, and under a sun 30% fainter than today, with no mechanism to escape the ice albedo trap, that frozen state appears to be permanent. The oceans would never thaw. Life would never have arisen. You would not be watching this video. The person who first put a precise number on this contradiction was Carl Sagan. The same Carl Sagan who would later become the most famous science communicator of the 20th century, the author of Cosmos, the voice that described Earth as a pale blue dot. In 1972, Sagan and his colleague George Mullen sat down with the best available models of stellar evolution and the best available evidence of Earth's ancient climate and calculated, for the first time with genuine rigor, just how cold the early Earth should have been. The answer disturbed them. Sagan was not a man easily disturbed by counterintuitive results. His career was built on following evidence wherever it led, regardless of how strange the destination. But the faint young sun calculation was different. It was not strange in the sense of being exotic or speculative. It was strange in the sense of being brutally, inescapably concrete. The physics of how stars generate energy through nuclear fusion was well established. The relationship between stellar luminosity and surface temperature was well understood. The greenhouse properties of the main atmospheric gases were known. You did not need exotic assumptions to get to the terrifying answer. You just needed to do the arithmetic correctly. And when Sagan and Mullen did the arithmetic correctly, the early Earth was frozen, not chilly, not cool. Frozen solid, with a global mean temperature well below the freezing point of water, in a state that the ice albedo feedback would have made permanent. What made the calculation particularly haunting was the geological evidence sitting directly alongside it. By 1972, geologists had already documented that the Archean eon, the interval from roughly 4 to 2.5 billion years ago, was characterized by active sedimentation in liquid water, by the presence of stromatolites that required shallow sunlit seas to grow, and by isotopic evidence indicating temperatures comparable to or warmer than the modern world. The contradiction was not ambiguous. It was sharp, clean, and impossible to dismiss. Sagan and Mullen named it the faint young sun paradox, and in doing so they handed the scientific community a problem that would not be solved quickly or easily. 50 years later, researchers are still working on it. The calculation itself rests on a foundation of stellar physics that is worth understanding in some detail, because the solidity of that foundation is precisely what makes the paradox so uncomfortable. Stars like the Sun are what astronomers call main sequence stars. They generate energy primarily through the fusion of hydrogen to helium in their cores, and they spend the vast majority of their lifetimes in this relatively stable state. The Sun has been on the main sequence for approximately 4.6 billion years and will remain there for approximately another 5 billion years. During this entire interval, it will continue to brighten at a rate of roughly 10% per billion years, driven by the progressive accumulation of helium in the core and the resulting increase in fusion rate. This brightening rate is not derived from a single observation of the Sun. It is derived from observations of thousands of stars of similar mass and composition to the Sun at different stages of their evolution that collectively map out the evolutionary track of a solar-type star across billions of years. It is also confirmed by the mathematical theory of stellar structure, which makes specific predictions about how a star's luminosity evolves as a function of its helium abundance. The theory and the observations agree closely. The 30% dimmer young sun is not a theoretical artifact that could be wished away by a different model. It is a robust observational and theoretical result that the scientific community has high confidence in. The first candidate solution Sagan and Mullen proposed in that same 1972 paper was ammonia. Ammonia is a potent greenhouse gas. It absorbs infrared radiation with considerable efficiency and can warm a planetary surface significantly, even at relatively low concentrations. Sagan and Mullen proposed that the early Earth's atmosphere contained enough ammonia to compensate for the reduced solar input, keeping the surface above freezing despite the dim sun. It was a reasonable hypothesis, and it dominated discussion of the paradox for about a decade. Then the problem became clear. Ammonia is not stable in an atmosphere exposed to ultraviolet radiation. The young sun, despite being dimmer in total energy output, was considerably more active in its high-energy ultraviolet emissions, the same violent solar activity that characterizes young stars, and that strips away planetary atmospheres if a planet lacks a protective magnetic field. Ultraviolet photons at the right energy will split ammonia molecules apart within approximately a decade of residence time in the upper atmosphere. For ammonia to serve as the solution to the faint young sun paradox, the early Earth would have needed to be replenishing its atmospheric ammonia supply at an extraordinary rate, faster than any known geological or biological process could sustain. The ammonia hypothesis fell apart, and the faint young sun paradox was left without a satisfying solution. The search for a replacement focused increasingly on carbon dioxide. Carbon dioxide is the most important greenhouse gas after water vapor, and unlike ammonia, it is stable in the atmosphere against ultraviolet destruction. The early Earth had abundant sources of carbon dioxide. Volcanic outgassing from the young, tectonically hyperactive interior was releasing CO2 at rates that were almost certainly higher than today. And crucially, the early Earth had essentially no sink for carbon dioxide that is now provided by life. No forests absorbing CO2 through photosynthesis, no vast quantities of calcium carbonate being deposited in oceanic sediments by shell-building organisms, no complex organic carbon being buried in marine sediments. The atmospheric CO2 concentration of the early Earth may have been, by some estimates, between 10 and 2,000 times higher than the current level of approximately 421 parts per million. The arithmetic of greenhouse warming is well understood. Carbon dioxide absorbs infrared radiation in specific wavelength bands and re-radiates it in all directions, including back toward the surface. At sufficiently high concentrations, it can provide substantial warming. The question for the faint young sun paradox is whether there was enough CO2 in the early atmosphere to compensate for 30% less solar energy. The honest answer, which has emerged from decades of increasingly sophisticated climate modeling, is probably not enough on its own. The problem is not that CO2 is an ineffective greenhouse gas. It clearly is effective, as our current situation with rising atmospheric CO2 demonstrates. The problem is one of scale. To compensate for 30% reduced solar luminosity, using CO2 alone would require concentrations somewhere between 10 and 100 times modern levels, depending on the specific climate model used. And while those concentrations are plausible for the very early Earth, the geological evidence for CO2 levels in the late Archean, the period from roughly 3 to 2.5 billion years ago, is considerably more ambiguous. Ancient soils called paleosols preserve chemical signals that can be interpreted as evidence for atmospheric CO2, and some analyses of Archean paleosols suggest that CO2 levels were actually lower than what the warmth observed in the geological record would require, if CO2 were the only greenhouse gas doing the work. This is where methane enters the story, and it enters as one of the most elegant and counterintuitive solutions in the history of Earth science. Methane, the simplest hydrocarbon, CH4, the same gas that makes up natural gas and is emitted by cattle and rice paddies and thawing permafrost, is a potent greenhouse gas. Over a 20-year timescale, it is approximately 84 times more effective at trapping heat than CO2. In today's atmosphere, methane is a minor greenhouse gas because it is present in only trace quantities, approximately 2 parts per million, and because in an oxygen-rich atmosphere, methane is chemically unstable. The hydroxyl radical OH, produced by the reaction of ozone with water vapor in the presence of ultraviolet light, attacks methane molecules and oxidizes them to CO2 and water on a timescale of roughly a decade. But here is the crucial point. The early Earth had no oxygen. The Great Oxidation Event, the irreversible oxygenation of Earth's atmosphere by photosynthetic cyanobacteria, did not occur until approximately 2.4 billion years ago. For the first 2 billion years of Earth's history, the atmosphere was anoxic, and without oxygen there is no ozone layer. And without an ozone layer, there is no efficient production of hydroxyl radicals. And without hydroxyl radicals, methane is stable in the atmosphere for approximately 10,000 years, rather than 10 years. In an anoxic atmosphere, the methane lifetime is roughly 1,000 times longer than in today's atmosphere. The implications are profound. On the modern Earth, biological production of methane by methanogenic archaea, single-celled organisms that consume hydrogen and carbon dioxide and exhale methane as their metabolic waste, is substantial. Methanogens are ancient organisms that evolved early in the history of life, and in the anoxic Archean Ocean, they would have thrived in environments that would kill any oxygen-dependent organism today. If the Archean methanogens were producing methane at rates comparable to modern biological methane production, which is a conservative assumption given their unconstrained access to an anoxic world, the result in an atmosphere with a 1,000 times longer methane lifetime would have been atmospheric methane concentrations on the order of 1,000 times modern levels. 1,000 parts per million of methane in an anoxic atmosphere would have provided substantial greenhouse warming, enough, in combination with elevated CO2, to keep the early Earth's surface above freezing despite the faint young sun. James Casting of Penn State University, one of the foremost researchers on early Earth climate, has argued for decades that the methane-CO2 combination is the most probable solution to the faint young sun paradox. His models, and those of his collaborators, show that with plausible early Archean concentrations of both gases, the surface temperature can be maintained in a range consistent with the geological evidence: liquid water, active sedimentation, and life, without requiring any exotic or implausible mechanisms. The methanogen story also has a beautiful internal consistency. The same organisms that produced the methane that kept the early Earth warm were also the earliest contributors to the biological complexity that would eventually transform the planet. Life was not merely a passenger on the warm early Earth. Life was one of the engineers that kept it warm. The methanogenic archaea deserve a proper introduction because they are among the most ancient and most underappreciated organisms on Earth. They are not bacteria. They belong to the domain Archaea, one of the three fundamental domains of life alongside bacteria and eukarya. And they represent an evolutionary lineage that almost certainly predates the split between bacteria and archaea, making them among the oldest continuous biological lineages on the planet. They live today in environments that would be instantly lethal to most familiar life. The oxygen-free sediments of lake bottoms and ocean floors, the digestive tracts of cattle and termites and humans, the hot springs of Yellowstone, and the deep crustal rocks kilometers below the surface of the continents. The one thing they all share is the requirement for an anoxic environment, because molecular oxygen poisons their metabolism. Methanogens produce methane as the end product of their metabolism. Different species use different substrates. Some consume hydrogen and carbon dioxide, some consume acetate, some consume methanol, but the output is always methane. In an anoxic atmosphere like that of the early Earth, every molecule of methane they produced would have persisted in the atmosphere for thousands of years, rather than the decade it lasts today. The early Earth's atmosphere would have smelled, if you could somehow transport a modern human there, profoundly and unmistakably of natural gas, the same organic odor that leaks from gas pipelines and rises from swamps and emanates from the mud of coastal marshes. That smell is the smell of the planetary thermostat doing its work. The discovery that ancient methanogens might have been climate engineers was not an obvious insight. It emerged gradually from the intersection of microbiology, atmospheric chemistry, and climate modeling over the course of the 1980s and 90s, driven primarily by the work of James Casting and his collaborators at Penn State. Casting's approach was to ask a deceptively simple question. If you put a realistic early Earth atmosphere into a sophisticated one-dimensional climate model with realistic estimates of volcanic outgassing rates and plausible early biological methane production, does the model produce a temperature consistent with what the geological evidence shows? The answer, after years of refinement, was yes, but only if the methane contribution from early life was included. CO2 alone, at geologically plausible concentrations was not enough. Add the methane that a world full of anoxic methanogens would have produced, and the numbers worked. Take the methane away, and the early Earth froze. This result had a profound implication that took some time for the field to absorb fully. The habitability of the early Earth may have depended not just on planetary-scale geophysical processes, volcanism, tectonics, the carbonate-silicate cycle, but on the biological activity of the simplest and most ancient organisms on the planet. The methanogens did not evolve in order to keep the Earth warm. They evolved to eat and reproduce in the anoxic environments available to them. But in doing so, they produced methane that accumulated in the atmosphere and enhanced the greenhouse effect. And that greenhouse effect maintained the warm conditions in which the methanogens themselves thrived. It was not planning. It was not cooperation. It was the simplest and most profound kind of feedback. Organisms modifying their environment in ways that supported their own persistence. There is, however, a complication with methane that has bedeviled the hypothesis from the beginning. Methane and nitrogen, in the presence of ultraviolet radiation, can react to produce complex organic molecules, a class of compounds known as tholins, the same chemistry responsible for the orange haze visible on Saturn's moon Titan. On the early Earth, with no ozone layer to absorb UV radiation, a methane-rich atmosphere might have produced a photochemical smog, an organic haze, that would have had complex and potentially contradictory effects on the planetary climate. Organic haze absorbs ultraviolet radiation, which would have been beneficial for the organisms living on the early Earth's surface. But it also scatters visible light, potentially reducing the amount of solar energy reaching the surface and partially offsetting the greenhouse warming it was supposed to provide. The net climatic effect of an organic haze depends critically on the precise properties of the haze particles, their size, their composition, their optical properties, all of which are difficult to constrain for conditions that existed 3 to 4 billion years ago. More recent research has added additional candidates to the solution set. Hydrogen gas, H2, is not typically thought of as a greenhouse gas because it does not absorb infrared radiation efficiently on its own. But at high enough concentrations, hydrogen can produce what physicists call collision-induced absorption. When two hydrogen molecules collide in the atmosphere, their collision temporarily distorts their electron clouds in ways that allow them to absorb infrared radiation that neither molecule could absorb individually. The same effect operates for nitrogen-nitrogen and nitrogen-hydrogen collisions, which means that a nitrogen-rich atmosphere at higher pressure than today would also have enhanced the greenhouse effect. Some models of the early Archean atmosphere include substantially higher nitrogen pressures than the modern atmosphere, reflecting the possibility that nitrogen now stored in Earth's crust and mantle was then present in the atmosphere. And these models find that the enhanced collision-induced absorption provides meaningful additional warming. In December of 2025, a research team tested one additional candidate with a detailed atmospheric chemistry model. The molecule nitrous oxide, N2O, sometimes called laughing gas, is a powerful greenhouse gas, and the researchers wanted to know whether the energetic particles emitted by the young active sun could have produced enough N2O in the early atmosphere to contribute to warming? The answer, unfortunately for the N2O hypothesis, was a clear no. Even under the most favorable assumptions, the space weather-produced N2O provided less than half a degree of surface warming, far too little to make a meaningful contribution to resolving the paradox. This kind of negative result is as scientifically valuable as a positive one. It narrows the solution space and directs attention to the mechanisms that actually matter. While the atmospheric chemistry debate has occupied much of the research community, a separate line of investigation has been asking a more fundamental question. Is the paradox actually as severe as the original Sagan and Mullen calculations suggested? The answer, it turns out, is that several factors reduce the severity of the problem in ways that were not appreciated in 1972. The first of these is the planetary albedo. Sagan and Mullen's original calculation assumed that the early Earth had roughly the same reflectivity as the modern Earth. But the modern Earth's high albedo reflects the contribution of continents, large land masses covered in relatively bright soil, vegetation, and rock, and of extensive cloud cover over those continents. The early Archean Earth was very different. In 2025, a study published in AGU Advances revisited the question of the early Archean Ocean using updated models of mantle temperature and water partitioning. The findings suggested that because the early Archean mantle was substantially hotter than today's mantle, the mantle's minerals had a reduced capacity to hold water in their crystal structures, meaning that more of the Earth's water budget was on the surface rather than in the interior. The early Archean Earth may have been a true water world, a planet almost entirely covered by ocean, with only scattered volcanic islands breaking the surface. An ocean-dominated planet would have had a dramatically lower albedo than the modern Earth. Dark ocean absorbs sunlight far more efficiently than bright continents. The lower albedo means more of the reduced solar energy was actually absorbed by the planetary surface rather than reflected back to space. This does not by itself solve the paradox. The reduction in solar luminosity is still a major problem, but it reduces the effective severity of the problem by perhaps 5 to 8 degrees Celsius, which is meaningful when you are trying to explain a temperature difference of 40 degrees. A second unexpected factor involves the Moon. 4 billion years ago, the Moon was substantially closer to the Earth than it is today. The Moon recedes from the Earth at approximately 1.5 inches per year, a consequence of tidal interactions between the Earth and Moon that gradually transfer angular momentum from the Earth's rotation to the Moon's orbit. Running this process backward, the Moon was perhaps half its current orbital distance from Earth during the early Archean, and possibly closer during the Hadean. A closer Moon means stronger tidal forces on the Earth, which means more tidal friction, which means more heat dissipated in the Earth's interior by the mechanical deformation of the crust and ocean. In a 2021 paper by René Heller and colleagues at the Max Planck Institute for Solar System Research, the tidal heating contribution from the early Moon was estimated at up to approximately 10 watts per square meter of Earth's surface over timescales of 100 million years, enough to raise the global mean surface temperature by up to 5 degrees Celsius. 5 degrees is not the complete solution to the paradox, but it is a meaningful contribution, particularly in combination with elevated greenhouse gases. A third factor that has received increasing attention is the thermal structure of the early atmosphere itself. In 2025, a new thermodynamic model published in the journal Climate by Xian-Wang Wu of Columbia University proposed that the climate sensitivity of the early Earth to changes in solar luminosity was substantially lower than conventional climate models assume. OU's model focused on the role of water vapor and clouds in setting the equilibrium temperature, arguing that intrinsic properties of water, specifically the exponential increase in saturated vapor pressure with temperature, act as a natural thermostat that limits the sensitivity of the climate system to external forcing. In his framework, the early Earth's lower solar luminosity would have driven a somewhat cooler and drier atmosphere. But the reduced evaporation and altered cloud properties would have partially compensated, preventing the runaway glaciation that simpler models predict. This thermodynamic closure theory remains controversial and has not yet been independently confirmed by other modeling groups, but it represents one of the most creative recent attempts to reframe the paradox in terms of fundamental atmospheric physics rather than specific gas concentrations. The geological record, meanwhile, continues to provide new evidence that complicates and enriches the picture. In April of 2026, a team of researchers published a study in Nature Communications Earth and Environment, describing the discovery of stromatolites in the Hapcheon impact crater in South Korea, relatively young structures compared to the Archean deposits of Australia, but significant for their preservation in a hydrothermal environment created by a meteorite impact. The finding reinforces the picture that life on early Earth was thriving in precisely the hydrothermal environments that were most abundant during the bombardment-heavy early Archean. Impact craters, mid-ocean ridges, volcanic hot springs, and that liquid water was continuously available in these environments even during periods when the global surface temperature may have dipped near or briefly below freezing. Life, in this picture, was not living on the knife edge of habitability. It was actively exploiting every warm and wet environment the young planet provided. The most important geological constraint on the faint young sun paradox, however, remains the evidence that the Archean Earth was not merely above freezing, but was in many respects warmer than the modern world. Isotopic ratios of oxygen and silicon in ancient marine cherts, fine-grained silica deposits formed in the early ocean, have been interpreted by some researchers as indicating that Archean ocean temperatures were actually quite hot by modern standards, perhaps 50 to 85 degrees Celsius, or 122 to 185 degrees Fahrenheit. If this interpretation is correct, the faint young sun paradox is not merely about keeping the Earth above freezing. It is about explaining warmth that substantially exceeds modern temperatures. The greenhouse effect required to achieve those temperatures under a faint young sun would be extraordinary even by the most optimistic atmospheric chemistry models. Not all researchers accept the hot Archean interpretation of the isotopic data. There are alternative explanations for the oxygen and silicon isotope ratios that do not require extremely high ocean temperatures. But the debate illustrates a feature of the paradox that is easy to overlook. We do not know precisely how warm the early Earth was. We know it was above freezing. We know life was present. We know liquid water was abundant. But the precise temperature of the Archean Ocean, and therefore the precise magnitude of the greenhouse effect that must be explained, remains uncertain. The faint young sun paradox is, in a very real sense, a paradox whose severity we cannot yet precisely measure. The element that ties all of these threads together is a mechanism known as the carbonate-silicate cycle, the geological thermostat that has regulated Earth's long-term climate for at least 3 billion years. And that provides the most satisfying framework for understanding not just why the early Earth was warm, but why it remained warm enough for life across billions of years, despite the continuously brightening sun. The carbonate-silicate cycle operates through the following loop. Atmospheric CO2 dissolves in rainwater to form weak carbonic acid. This acidic rain falls on silicate rocks, the dominant rocks of the continental crust, and chemically weathers them, releasing calcium and bicarbonate ions that are carried by rivers into the ocean. In the ocean, these ions are used by shell-building organisms to form calcium carbonate, which eventually settles to the seafloor and is incorporated into marine sediments. When these sediments are subducted into the mantle at tectonic plate boundaries, the heat and pressure of the mantle converts the calcium carbonate back to CO2, which is eventually released back into the atmosphere through volcanic eruptions. The cycle is thus: atmosphere, rain, silicate weathering, ocean, sediment, subduction, volcano, atmosphere. The average carbon atom completes this cycle in approximately 500,000 years. The beauty of this cycle for the faint young sun problem is the negative feedback it contains. If the Earth's surface temperature drops, as it would if the sun grows dimmer, the rate of silicate weathering decreases, because weathering is a chemical reaction that is sensitive to temperature and the availability of liquid water. Reduced weathering means less CO2 is being removed from the atmosphere. But volcanoes keep emitting CO2 at roughly the same rate regardless of surface temperature. The atmospheric CO2 concentration therefore rises, increasing the greenhouse effect and warming the planet back toward its equilibrium temperature. Conversely, if the temperature rises, as it does as the sun brightens over geological time, weathering rates increase, drawing down CO2, reducing the greenhouse effect and cooling the planet back toward equilibrium. The carbonate-silicate cycle acts as a planetary thermostat with a time constant of hundreds of thousands of years, automatically adjusting the atmospheric CO2 concentration to compensate for changes in solar luminosity or other climate forcings. The thermostat was already running during the Archean. It just had a very different setting. The carbonate-silicate cycle is not an abstract mechanism. You can see it operating today in slow motion in landscapes around the world. In the limestone karst regions of Kentucky, Tennessee, and the Yucatan Peninsula of Mexico, slightly acidic rainwater is slowly dissolving the calcium carbonate bedrock. opening caves and sinkholes and disappearing rivers that reappear kilometers away as springs. This is carbon dioxide from the atmosphere, dissolved in rainwater as carbonic acid, chemically attacking rock, a process that sequesters atmospheric carbon in dissolved bicarbonate ions that eventually reach the ocean. In the volcanic arcs of the Pacific Northwest, of Indonesia, of Japan, subducted marine carbonates are being heated and pressurized in the mantle and releasing their carbon as CO2 that rises through magma chambers and emerges at volcanic vents. The emissions from volcanoes like Mount St. Helens and Mount Rainier are, in part, the exhalations of ancient marine sediments returning their carbon to the atmosphere after tens of millions of years in the Earth's interior. The time constant of this cycle, the average residence time of a carbon atom in the geological reservoir before it completes the full loop from atmosphere to rock to subduction zone to volcano and back to atmosphere, is approximately 500,000 years. This is both a limitation and a strength of the mechanism. On timescales shorter than a few 100,000 years, the carbonate-silicate cycle cannot respond quickly enough to moderate climate changes. It is far too slow to have any effect on the carbon cycle perturbations of the Industrial Revolution, for example, which operate on timescales of decades to centuries. But on geological timescales, millions to billions of years, it is extraordinarily effective. A change in solar luminosity that occurs over hundreds of millions of years gives the carbonate-silicate cycle ample time to adjust atmospheric CO2 in compensation. This is precisely why the Earth has maintained habitable conditions across 4 billion years, despite a 30% increase in solar luminosity. The thermostat is slow, but it has had 4 billion years to work. The precise sensitivity of the carbonate-silicate thermostat, how much CO2 concentration changes in response to a given change in temperature or solar luminosity, depends on factors that are difficult to constrain for the early Earth. The area of exposed silicate rock available for weathering, the temperature dependence of the weathering reactions, the rate of volcanic outgassing, and the presence or absence of vascular plants, which dramatically accelerate weathering rates through their root chemistry. These uncertainties mean that while we can be confident that the carbonate-silicate cycle was operating on the early Earth, we cannot be precise about the atmospheric CO2 concentration it maintained at any given point in the Archean. The thermostat was working. The exact setting it chose, and whether it was sufficient on its own or required the assistance of methane and other greenhouse gases, remains an active area of research. The role of biology in this story deserves emphasis. The early methanogens that produced the methane greenhouse of the Archean were not merely passive beneficiaries of warm conditions. They were active participants in the climate system, generating a greenhouse gas at rates that helped maintain the warmth their own existence required. When photosynthetic cyanobacteria evolved and began producing oxygen approximately 2.7 to 2.4 billion years ago, they transformed the atmosphere in ways that destroyed the methane greenhouse, because oxygen in the atmosphere rapidly oxidizes methane, and triggered the first global glaciation in Earth's history, the Huronian glaciation. This was not a coincidence. It was cause and effect. The Great Oxidation Event, one of the most consequential transitions in Earth's biological history, was simultaneously an act of climate catastrophe. Life changed the atmosphere. The atmosphere changed the climate. The climate changed the conditions for life. This is not a simple story of biology flourishing because the planet happened to be warm. It is a story of biology and climate co-evolving, sometimes cooperatively and sometimes at cross purposes, across billions of years. The faint young sun paradox does not exist in isolation. It is the Earth chapter of a problem that affects the entire solar system. Mars, our nearest planetary neighbor, also experienced the faint young sun of the early solar system. And Mars has its own version of the paradox. The ancient southern highlands of Mars, the oldest exposed terrain on the planet, preserve abundant geological evidence of liquid water, river valleys, lake beds, delta deposits, and minerals that can only form in the presence of liquid water. The Noachian period of Martian history, roughly 4 to 3.7 billion years ago, was a time when Mars had liquid water on its surface, rivers flowing, lakes filling impact craters, and possibly a shallow northern ocean. This is the Martian equivalent of the Archean evidence on Earth, and it presents exactly the same problem. Under the faint young sun, with the thin CO2 atmosphere that Mars is thought to have had, even Mars, which is 50% farther from the Sun than Earth, and therefore receives only 43% as much solar energy, should have been frozen solid. The resolution of the Martian version of the paradox has proven even more elusive than the Earth version, because Mars presents an additional challenge. It eventually did freeze. Unlike Earth, which has maintained liquid water at its surface continuously for at least 4 billion years, Mars transitioned from a relatively warm and wet world in the Noachian to the cold, dry, frozen planet we observe today. Something ended the Martian warm period. The leading candidates are the loss of Mars's magnetic field, which allowed the solar wind to gradually strip away the Martian atmosphere, removing the greenhouse gases that had been maintaining surface warmth, and the gradual decline of Martian volcanism, which reduced the rate of CO2 outgassing that had been compensating for atmospheric loss. Earth avoided this fate because of its size. Earth's larger mass retained its internal heat longer, sustaining volcanism and the magnetic field that protects the atmosphere. And Earth's stronger gravity held its atmosphere against solar wind, stripping more effectively than Mars could. The comparison between Earth and Mars is not merely a historical curiosity. It is directly relevant to the question of life in the universe. The faint young sun paradox tells us something profound about what it takes for a planet to maintain habitable conditions across the multi-billion-year timescales that the evolution of complex life apparently requires. Earth succeeded, barely, and with the assistance of a suite of factors: elevated greenhouse gases, lower albedo, tidal heating, the carbonate silicate thermostat, and ultimately biology itself. that collectively kept the surface temperature within the habitable range. Mars failed, and the margin between success and failure was not enormous. The same planetary processes that saved Earth were operating on Mars, but in insufficient measure. For astrobiologists, the researchers who study the conditions necessary for life and the likelihood of finding it elsewhere, the faint young sun paradox has important implications for the concept known as the habitable zone. The habitable zone around a star is conventionally defined as the range of orbital distances at which a planet could have liquid water on its surface, given a certain atmospheric composition and assuming a certain planetary size and composition. The inner edge of the habitable zone is set by the runaway greenhouse effect. Too close to the star and water vapor feedback drives the planet to a Venus-like hell. The outer edge is set by the maximum greenhouse effect achievable with CO2. Too far from the star, and even a thick CO2 atmosphere cannot provide enough warming to maintain liquid water. But the faint young sun paradox reveals a complication that the simple habitable zone concept does not capture. A planet's habitability is not a static condition determined solely by its distance from its star. It is a dynamic outcome of the interactions between the planet's interior, its atmosphere, its oceans, and any biology that inhabits it. A planet that is habitable today might not have been habitable 3 billion years ago under the same star's earlier, dimmer output. A planet that is habitable for the first 100 million years of its host star's life might become uninhabitable as the star brightens and the carbonate silicate thermostat fails to draw down CO2 fast enough. The temporal dimension of habitability, whether a planet can maintain habitable conditions for long enough for complex life to evolve, is as important as the instantaneous assessment of whether conditions are within the right range. There is one final dimension of the faint young sun paradox that deserves attention: the fact that it is not fully solved. After 50 years of intensive research, we have a rich collection of candidate solutions, each of which provides part of the answer. Elevated CO2 almost certainly helped. Elevated methane from methanogenic archaea almost certainly helped more. Lower planetary albedo from an ocean-dominated world helped. Tidal heating from a closer moon helped a little. The carbonate silicate thermostat maintained the balance over geological time. Some combination of these factors, the exact combination remains uncertain and debated, kept the early Earth warm enough for liquid water and life throughout the 4 billion years since those Jack Hill zircons were formed. But no single clean solution has emerged, and the hypothesis space remains contested. Researchers cannot agree on whether the late Archean Ocean was 50 degrees warmer than today or only modestly warmer. They cannot agree on whether elevated CO2 was sufficient to explain the warming or whether methane was essential. They cannot agree on whether the organic haze produced by a methane-rich atmosphere would have been a net warming or cooling factor. The paradox has been tamed, but not vanquished. I think this is worth celebrating rather than lamenting. Science is not most productive when all the major questions are settled and all the models agree. Science is most productive when there is a genuine puzzle that multiple lines of evidence constrain but do not fully solve. When the answer is tantalizingly close but not yet in hand. The faint young sun paradox has been one of the most productive puzzles in the history of Earth science, generating insights into stellar physics, atmospheric chemistry, marine geochemistry, early life, planetary habitability, and the deep history of the solar system. Every attempt to solve it has produced collateral knowledge about how the Earth actually works. Consider what the paradox forced us to learn. We now understand the carbonate-silicate cycle and its role as a planetary thermostat in a way that we could not have appreciated without the pressure of explaining 4 billion years of continuous habitability. We now understand the role of methanogens as climate engineers of the early Earth, a role that was completely invisible before the faint young sun problem forced researchers to think seriously about the climate effects of early anaerobic life. We now understand the connections between the Great Oxidation Event and the first global glaciation in a way that required both atmospheric chemistry and climate modeling to disentangle. All of this knowledge came from trying to understand why an ancient, anemic sun did not freeze a planet that had no business staying warm. In the Jack Hills of Western Australia, those 4.4 billion-year-old zircon crystals are still there, in rocks that look utterly unremarkable to a non-geologist. Grey, weathered, not particularly dramatic in the way that the Grand Canyon or Yellowstone are dramatic. But inside those tiny crystals is the oldest physical evidence of a planet that defied physics. That kept its oceans liquid against all theoretical expectation, that maintained the conditions for life through the coldest, most hostile period of its history. Whatever combination of greenhouse gases and lower albedo and tidal heating and geochemical feedbacks managed to keep those ancient oceans from freezing, it did something extraordinary. It gave life a chance. And life, once given that chance, was not passive. It joined the climate system as an active participant, produced greenhouse gases that amplified its own warmth, transformed the atmosphere through photosynthesis, and eventually evolved into organisms capable of looking back 4.5 billion years and asking why the math didn't work out the way it should have. The faint young sun paradox is, at its deepest level, a story about the improbable persistence of habitability on a planet that had every reason to fail. It is worth sitting with that improbability for a moment. The factors that collectively maintained the habitability of early Earth were not in any sense guaranteed. The elevated CO2 required active volcanism at rates sufficient to outpace weathering, rates that depend on the details of early plate tectonic activity that we cannot directly observe. The methane greenhouse required the early evolution of methanogens and their widespread deployment in the anoxic early ocean. An evolutionary event that could, in principle, have happened later, or not at all. The lower planetary albedo from an ocean-dominated surface required that Earth's water budget exceed a certain threshold, and that the early mantle be hot enough to push water from the interior to the surface, conditions that depend on the details of Earth's formation and early evolution. The tidal heating from the early moon required that the Moon form in a specific range of orbital configurations, and that it form early enough to contribute meaningfully to the Hadean and early Archean heat budget. None of these factors were inevitable. Each of them was contingent on prior conditions and events. This contingency is what makes the comparison with Mars so instructive. Mars received the same faint young sun. Mars had volcanism that outgassed CO2. Mars had a period of early warming sufficient for liquid water. But Mars lacked something, or several somethings, that Earth had. Mars's smaller size meant its interior cooled faster, shutting down volcanism and the resupply of greenhouse gases before the carbonate silicate thermostat could establish a stable long-term equilibrium. Mars's smaller size also meant it lost its magnetic field sooner, allowing the solar wind to gradually strip away the atmosphere that had been maintaining the early warmth. Mars had no large moon to provide tidal heating. Mars may have had a thinner initial water inventory, limiting the ocean coverage that reduced Earth's albedo. The list of differences is long, and each difference points in the same direction, away from long-term habitability. The contrast between Earth and Mars is a natural experiment in planetary habitability that we are only beginning to fully analyze. The Mars Perseverance rover, currently exploring the ancient delta deposit in Jezero crater, is reading the geological record of a planet that was habitable in its youth and became uninhabitable in its middle age. Every sedimentary layer it drills, every mineral signature it analyzes, every organic compound it detects or fails to detect adds a data point to our understanding of what separates a planet that stays warm and wet from one that freezes and desiccates. The faint young sun paradox is not just Earth's problem, it is the solar system's problem. And solving it fully, rigorously, with all the quantitative precision that the question deserves, will tell us not just about our own planet's past, but about the likelihood of finding other worlds that stayed warm and wet long enough for life to become complex. Physics said frozen. Geology said warm. And somewhere in the space between those two facts, in the chemical complexity of an ancient atmosphere and the warm black expanse of a young ocean under a pale sun, the conditions for everything that followed were preserved.